Alkanes are saturated hydrocarbons with only carbon and hydrogen atoms. The nomenclature, aka the naming system, depends on the number of carbon in the chain. Each is followed by ane as a suffix. So we have methane, ethane, propane, butane, pentane, hexane, heptane, so on. All the carbons in the chain are sp3 hybridized, which means the orbitals take the shape of a tetrahedron. The exact details should be covered by a separate video. In general, it is the lowest energy state geometry. If you put the chain in the plane of the paper, the two hydrogens on each carbon should point in and out of the plane. The chains can branch. In that case, count the longest straight chain possible, redraw the molecule such that the longest chain is in a straight line, label the carbons, and reattach the side chains. To name the branched molecule, you start by naming the longest chain. In this example, the longest chain is 5, so I have a pentane. Now look at the side branch. Each side branch is named by their carbon number, followed by YL as a suffix. Here we have an ethyl side chain. Finally, to describe where it was attached, we add an Arabic number in front. Hence, the molecule here is called 3-ethyl pentane. There are two other rules for naming, first of which is that you should use duplication prefix for multiple identical side chains. The second is use the lowest number possible. So for this molecule, instead of calling it 4-methyl 3-methyl pentane, it's called 2,3-dimethyl pentane. Alkanes are stable hydrocarbons. There isn't a lot of reaction relevant due to its lack of functional groups, but we can use radicals to break them open. The first reaction is cracking, the process of converting high-mass hydrocarbons into low-mass hydrocarbons. This is a great way of utilizing natural resources since long-chain hydrocarbons are messy, difficult to manipulate, and have very limited uses versus short-chain hydrocarbons. Step 1. High heat forces a carbon-carbon bond to break, resulting in the formation of two alkyl radicals. The radicals proceed to react, forming a new CH bond at the cost of another. The radicals then combine and form two stable molecules, an alkane and an alkene. This can also happen by breaking a CH bond at the start, which will make a hydrogen molecule and an alkene. The second reaction is a free radical substitution. A halogen molecule is activated by UV light, a step called initiation. The Cl radical can steal a hydrogen atom off the alkane, forming an alkyl radical. This alkyl radical eventually finds another Cl radical and recombine, forming the haloalkane, and so terminates the reaction. This radical approach is not a controlled process. It is very likely that the alkane will be turned into many different versions of the substituted species. Hence, it is much more often made by chemical suppliers in big bulk, refined, and sold as starting reagent for other chemists. Haloalkanes can be used in many reactions such as nucleophilic substitution, making Grignard reagents, elimination, and much more, which is a topic for another video. Thanks for watching. I'll see you next time.